Hi, I'm Ben-Yaakov. This presentation is entitled PSPICE Add-on Simulation Model, Ferrite Core Losses and Hotspot Temperature Estimation. Now, a limiting factor in the design of inductors and transformer is the losses in the core, in the ferrite core. And this information of losses in ferrite cores is given usually by manufacturers as this. In this case, we're seeing this is the loss in kilowatt per meter cube. This is equivalent to milliwatts of centimeter cube as a function of the excitation of the magnetic flux density excitation. The hat means peak value. So for example, here we have 100 millitesla peak value, and say for 100 kilohertz or say 200 kilohertz, it will be about say 200 milliwatts. Okay, so these are straight lines when this information is given in a log-log scale, where this is the power loss per volume, and this is the peak magnitude of the flux density, and these are the frequencies. Now notice that this is of course for one particular material. Each material will have its own chart. This is 3F3, and this is also correct for one particular temperature. Okay, so this is 100 degrees centigrade. Now the dependence of this core losses, of ferrite core losses, the function of temperature, is usually given in this kind of a chart. We see here temperature and points of frequency and flux density. So say 200 kilohertz, 100 millitesla. This is the point we've looked earlier, and at 100 degree, indeed, this is 200. This will be milliwatts per centimeter cube. For other pairs like 400 kilohertz and 50 millitesla, this is this curve, etc., etc. So by combining this chart and this chart, one can actually get the core losses at any given operating condition of the core. Now the curve that we have seen, in particular this one, is actually obtained by fitting data to this equation, which is the Steinmetz equation, which relates the power loss per volume as a function of frequency and flux density. K is a constant, A is a constant, and B are constant. This is an empirical equation, and the way these constants are obtained is by fitting data. Now the data is measured by sinusoidal excitation and with no DC. Now DC bias, which moves the B flux density upward into the hysteresis loop, is known to increase losses. However, this information is not available widely, certainly not for all the cores. So in most cases, designers are just assuming that this represents the situation. This is maybe okay in the case of a transformer, which usually will not have a DC bias, but in case of an inductor, this is just an approximation, an estimation of the core losses. The DC component of the flux density will affect the value, will increase it, in fact, the core loss. Now in this presentation, I'm going to show how this equation, which is the Steinmetz equation, can be incorporated in a SPICE simulation as part of the overall simulation of, say, a PWM converter or any other converter, switch mode converter. And by adding this part into the simulation schematics, one can obtain on the fly the value of the losses, okay? Uh, this will not interfere with the regular simulation. You get this information as operating conditions are changing. However, like the basic Steinmetz equation, it does not include the DC effect. That is, it is a first order estimation of the core loss. And it is also assuming, in this presentation that I'm showing, that the constants of the equation, Steinmetz equation, are fixed. That is, we know that these constants are, first of all, function of temperature, as I've shown earlier, and also for different frequency ranges, these constants are a little bit different. So in the model or simulation model that we are going to discuss, we are just assuming constant value for K, A, and B, which of course I assume to be known, and this information usually is given by manufacturer. You can find it in data sheets and in many other documents that are available online. Another feature of this model, of this simulation model that I'm going to show, is that you can actually get an estimation of the hotspot of the element, of the magnetic element, being either a transformer or an inductor. Now, it has been known that you can approximate the value of this hotspot within the element by this equation. This equation says that you have to get the total power loss of the element. Now, the total power loss includes both the core loss and the so-called copper loss. That is the heating of the wires, okay? So this is the total power dissipation of this element. AS is the surface area of this element. That is the surface area all around the element. And to the power of 0.833, this is again an empirical equation that is being used to estimate the hot spot. So again, this is another add-on for the simulation. Again, it doesn't interfere with the simulation. You can get the result as soon as the conditions are changing. However, it's an approximate, of course, estimation of the temperature. And the copper loss are calculated by this simulation model that I'm going to show you by this equation, which is the RAC. This is the resistance of the wire at the high frequency of operation times I square, okay? So the R times I square. Now, this does not take into effect the proximity effect, does not take it into consideration. RAC has to be modified to take this proximity effect into account. Now, in this model that I'm showing, I'm just assuming that you have this RAC available. And as a first approximation, you can get it from the skin effect. Of course, a more elaborate calculation will give you also taking into account the proximity effect. I'm assuming that you know this value, and once you know it, you can calculate the copper of the element. Okay, we see here the schematics, and I'll go over the various parts. Let me first of all start, I'll zoom it a little bit so we can easily see what's going on, and I'll start with the parameters, okay? The simulation that I'm showing is for an inductor. We assume 50 turns. These are the parameters of the core. This is the volume. This is the cross-section area of the core. LE is the magnetic length, path length. K, A, and B are the Steinmetz constant. R, well, this is not related to the model. Area is the surface area of the element, assumed to be 20, this is in centimeter square. RAC, 50 milliohm, assumed to be known. And in this case, this is just a parameter which will be changed. Frequency 200 kilohertz. The the amplitude of the excitation is 200 volt, and uh, this is the peak value of the flux density, and the reason that it is put in the parameter is because what I've done here is that I've defined the amplitude of the source. This is the source. I've defined it as a function of bk, so that by sweeping this value, it will automatically calculate the amplitude that will generate the peak value, so that I'll get all the information as a function of the flux density, which is more convenient for just illustration. Okay, so this source of excitation of this is the device under test, you might say, although our AC is part of it. This is used just for measuring the current. It's a known way for measuring current in SPICE. It's a voltage source of 0 voltage, so the current through it can be identified. So this is the device under test, 250 microhenry, and this is the excitation at one point. We are going to sweep it later on. So now this is device under test. Now what we are doing here is we are measuring the voltage across the inductor and calculating actually the flux density by the state space equation. What this thing says is that is the integral of the input of the voltage divided by the number of turns and the cross-section area of the core. So this actually calculates B, the total B of the core, by measuring voltage and taking the integral of it. Now, since we are going to use the Steinmetz equation, which is only correct for the AC component, there is a high-pass filter here, so that at the end of it, we're going to get just the AC component of the flux density. Okay, so BAC is the magnetic flux density, the AC component of which, of course, this should be at a lower frequency as compared to the switching frequency, or the excitation frequency, I should say, in this particular case. Okay? Now, once we have this value, we need the peak value for the equation. Okay? The Steinmetz equation needs the peak value. Here we're going to see a time-dependent value. In order to get the peak value, I've put here a peak detector. Okay? Now there is an issue here because there is a voltage drop on this diode, and therefore you may not get the exact peak value. In order to overcome it, I've amplified this signal 1000-fold. Okay? So this is the high voltage going to be here. So therefore the voltage drop across the diode is really negligibly small as compared to the high voltage here, and then later on I'll divide it back to get the correct value. Okay, so this is just a trick to get rid of this voltage drop of the diode. I could have designed the diode with 0 voltage drop, but I prefer to do it this way. So now on this peak detector, we're going to have the peak value of the magnetic flux density during this simulation. Okay, this is a sort of a DC value here, getting just the peaks. Okay, now we have the information of the value, and we can move actually to the Steinmetz equation. Here it is. It is in the syntax of PSPICE. So we have K is the constant. This is frequency to the power of A. This is the peak value to the divided by 1K, because we have to get back to the real value, to the power of B. Now this is power per volume, so I'm multiplying it by the volume. So P now is the total core loss. Okay, the total core loss for this element. Now I'm calculating the copper loss. I'm assuming that RAC is known. This IV2 is the current through this voltage source of V2. So here we have this product. This is a pulsating value waveform here because this is time dependent. V2 is the current is time dependent because this is a sinusoidal waveform. And to get the average value, there is a low pass filter here. And so this is the average value of the copper loss. Okay, now I combine these two together. So we have the um, core loss, the copper loss, and since this is in watts, I need it in milliwatts. So it's multiplied by 1,000, divided by the area, and to the power of 0.833. So this point is really the average temperature rise in centigrade above ambient, using this, of course, approximate equation. Okay, so let's just not have a look at the whole thing again. We see, again, these are the parameters. This is the core data. This is the Steiners equation data, the constant, RAC, etc., excitation, device under test, uh, flux density calculation, peak value, Steinmetz equation, copper loss, and temperature rise. Okay, so let's give it a try and see what's happening here. Okay, here we have it. Let's start from here. This is the voltage across the inductor. Okay, this is the current through the inductor. Well, the reason that there is a DC through the inductor is because of the initial condition. The question is, where do you start the voltage? If I would have started at 90 degree, the DC would be 0, but this really doesn't hurt us because BAC, this is the AC component of the flux density, is of course an AC, a pure AC, and since I've specified Bmax to be 100 millitesla, that's what we are getting, plus minus 100 millitesla. Voltage has been adjusted to get this value. Now, the red one here is the peak value. This is just the peak value of the after the diode. And here we are going to we see the green one is the core loss, the 60 milliwatts. The red one, this is multiplied by 10 because it's a small value, and so therefore we don't see it if in its original value, so it's sort of multiplied so we can see it. And this is this component of the copper loss. This is the copper loss. Now, combining these two into the estimation of the hot spots, we get 18 degrees centigrade above ambient. Okay, so this is just the basic information that we are getting. Now, I can do a parameter run for a number of points. Let me do that. This setting, and let's have a look what it is. We see that I run it for 5 milliseconds, start to get the information from 4.25 milliseconds, so it's only the last 50 microseconds collecting the data. And the parameter here is the peak value. So I'm sweeping on the flux density, the peak value of the flux density from 10 millitesla to 400 millitesla with steps of 50 millitesla. Okay, so this is this setting, and let's have a look at it. Okay, so I've got now all these runs. I'll select all of them, and we see them now uh, in the time domain with the different amplitude, since we have done this parameter run. Now I'm going, however, to look at the performance evaluation. And here it is. Now what do we see here is the following. This is the accumulation of all the information. We have here on the horizontal axis, we have the peak flux density. So it's from 10 to a little bit above 300 millitesla. This is now, it's now divided by the volume. The total power is divided by the volume. So this is actually the core loss per volume, like you'll see it in the charts of the manufacturers, okay? So this is one curve, and I believe this is for 200 kilohertz. Now, I've actually run it for different frequencies, so I can now get this information and add it on. Let's do that. Okay, so this is now for 100 kilohertz. This is 200 kilohertz. Let's add some more. This is for 25 kilohertz. Okay, so this is the 25 kilohertz, and I believe we have some more here. Okay, so we got here family of curve. This is pretty much like the charts that the manufacturer are providing, and this was done by simulation using the Steinmetz equation, and then running parameter sweep on the flux density, and then using performance analysis. This is this knob here, to collect all this data and see it in this chart. And this is, by the way, a log-log scale, so this is exactly the way the manufacturer are providing it. Okay, now let's have a look now at another type of simulation. Okay, this is like a buck type circuit. We have now a square wave. We have an inductor. We have an output section. This is representing a load, and this is just a filter capacitor. And now we are looking at the inductor of this sort of model of a buck converter. And let's see what's happening here now. This is, the rest of it is exactly the same. Okay, here it is. This is for this sort of buck model. We have here the voltage across the inductor. It is fed by 200 volt. The output and the duty cycle is 0.5, so the output is 100 volts. So we see plus minus 100 volt across the inductor. Now this is now the current through the inductor. Evidently there is a DC component, as it should be, because there is a DC load. And we see here the peak value. This is the green again. The blue one is the AC component of the B. The red one is the total B. Okay, there's a DC component here, but in the Steinmetz equation we cannot use it. We have to use just the AC component. So the blue one is the AC component, and the green is the peak value. And this is again the core loss, and this is the copper loss, and this is then the temperature rise. In this particular case, it came out to be 6 degrees above ambient. So this brings me to the end of this presentation. I thank you very much for your attention. I hope you have found it interesting and that it will be useful to you in the future. Thank you.